Out three different things that they're kind of nice problems to go over, I think, at this level. Your homework on 1.6, I think there's only like 4 problems on it, so they're pretty similar to these. Okay, so what we're going to look at to begin with is what the problem says is you have a rectangular piece of cardboard, and it's 30 by 15 inches. All right, and what you do is you're going to make it into a box that doesn't have a top. So we need to change this a little bit. This dimension, I took this picture out of the internet because it's a pretty good picture to visualize what's going on. So we got 30 inches and 15 inches like that. So that's your original cardboard. Okay, now what you're doing is you're taking these squares and you're cutting it out. And then if you fold it up, the flaps up, okay, you would end up with a box without a top. Does that make sense visually what I'm saying? Okay. So what we do on this is we're going to figure out with our calculator mostly is what is the way to cut those squares out that would make the box have the biggest volume possible. Okay, that's kind of a typical calculus problem that's called optimization. And what you want to do is you want to build a function out of that in order to do that then. So here's the idea. X is the size of the square that you cut out. So this first thing right here is you would have to figure out, after you cut that out, you would have to figure out what is the length of that. Okay, it starts 30, but what are you taking off of that? You're taking an X and another X, right? So what's X and X? What's the total? What's X plus X? Say something, okay? 2X, okay, right? So this piece right here is going to be 30 minus 2X. It started 30, and we chopped off 2 X's, right? Does that make sense? Okay, the whole part minus the part that we chopped off, okay? How about this piece right here? What would that be? It starts 15, what would it be? 15 minus 2X, right? It's the same thing, okay? So that piece right there is 15 times 2X, okay? Now, the other thing you got to know is what is the height. So what's the height of this? X, exactly, okay? So what you have is, remember, X is the part you fold up, X, so it's Xi like that, all right? Does that make sense dimension-wise? Okay, all right? How do you find a volume of like a box? What do you have to know? What 3 things? Length, width, and height. So the formula we have is volume is length times width times height. Okay, like that. Okay, so what you're going to do with this then is this is the length, that's the width, that's the height. It doesn't matter what order you put those things in. So our volume function is just going to be this. We'll say V of X, and then just multiply these together. I'm going to do the X first, because it doesn't matter what the length, width, and height is. You just have to multiply those dimensions like that. Okay? So that's the function that would model this. If you were a Calc 1 student, there's calculus you would do that would figure out what X value would make this box hold the biggest amount. Okay? So that's how that would go so far. Any questions so far about the setup or anything? Okay. Now, when I say feasible values of X, let's think about this for a minute and kind of think what would happen on this problem. Okay, first of all, let me ask this question right here and see if you understand this. Okay, what would be the biggest value of X that you could chop off if this side is 15? What would be the biggest thing? What? 7.5, right, okay. If you chopped off 7.5, well, you wouldn't have a box, right? You would basically destroy the whole thing, and then you would just have a flap that comes up, and you would have 0 volume. But anywhere from 0 to 15 is going to make a box. Even if that was 7.4, it would make a real tall, skinny box. Does that make sense to you? Okay. So what we're going to say on this is the feasible region, we would just say like this, okay? And really in parentheses, we would say 0 you wouldn't want to cut nothing out. Then you would just have a flat piece of paper. Then you would have 7.5, but don't include it, because if you included it, you would have just a piece of paper. You wouldn't be able to make a box out of it, okay? So now you want to get your calculator out, because the rest of the problem in pre-calc, you have to do this with your calculator, okay? So we want to go ahead and get stuff put in the calculator. And it's going to go like this. All right, so what you want to put in is you want to put in y1, you want to put the volume function in. Don't multiply it out. That's a waste of time to FOIL and all that stuff. It's unnecessary. So you want to just put in the function x, and then parentheses 30 minus 2x. And then you want to put in 15 minus 2x like that. Okay, then we'll have to set up a viewing window on this. Now, the other thing you got to do is you got to know how to think through the problem with your window. All right, so the first thing is the window. Remember the feasible region 0 to 7.5. So for your x's, you would just want to go 0 and then maybe to 8. You could go 7.5 also, but that's a part of the problem is you need to understand that the graph doesn't make sense once you get past 7.5. Okay, now the y values. How do you set your y values? Now this is the way you want to set up your y, is look at your table. So if you go second graph, look at your table, and that will tell you how the y values are changing. So I do this. All right, so if you look from 0 to 8, notice that you start at 0. It looks like the biggest number I ever see is 648. Then once you get past 7, so you start getting negative volume. It doesn't make any sense anymore. So I would probably say up to 700 as a result. So I'd make my y probably go 0 to 700. Okay, that's how you want to figure that out. Okay, so let me go ahead and put this in. And a good way to scale that would probably be by 100 would be kind of a logical way to do that like that then. Okay, so that would be a good logical viewing window to use. And once you get that put in, then graph it, and then this is what you're going to see. Okay, and the idea is x is what? That's the size of square you cut out. What is y? Y is the volume. So what's happening to the volume? It's getting bigger. It's reaching a top point. Then it goes down to nothing. So this makes sense to me. If x is 0, you don't even have a box. If x is 7.5, you don't have a box. Does that make sense? Okay, so you're going to figure out what that maximum is on that, so it kind of hits a high point and goes down like that. So on your graph, this is really about all I would want you to do on a graph, is just kind of label it, like this is x, and then this is y, and you'd want to say that's the volume. And let's see, that would be in cubic inches. Volume is cubic units. And then x would be in inches. Okay, and then just kind of, I'm going to do this like this. Just kind of mark it off like this so it's fairly big. 1, 2, 3, 4, 5, 6, 7. That's good enough. Okay. And then you've got, we're going to go all the way up to 700. So I'm going to go like kind of like this, 1, 2, 3, 4, 5, 6, 700. And then if you can just, label the first and second one and last one, and that's okay. All right. And then we're just going to get some points, and then I'll show you how to get the maximum. So clearly you have the 0.00 and you have the 7.50. Okay. Now, if this is new to you, this is the way you do a maximum on here. You follow what's in this box here. So what I'm going to do is once you get your graph, just watch how I do this and try it on your calculator. So you would go second and then trace. Then you're going to find option. Now this time it's a maximum. So you go to a maximum. Only do a min if you're looking for a minimum. Then you press enter. Okay. Then you're going to get what you call bounds. So a left bound, you're going to use your left cursor to just move the cursor until you get a little bit to the left of that high point. It doesn't matter where, it just needs to be a little to the left of it. Then press enter. Okay. Most calculators will kind of have a vertical line come out, and then do a right bound. So just move over to the right. Okay, press enter, and then when it says guess, you press enter and it should do it right. Okay. Right, so that will now give you the maximum. You know it's right because it'll be blinking on it and it'll tell you what the maximum is. All right, so here's what these numbers are. If you look at these two numbers on here, let's think about what these things represent. What is the 3.1 in the context of the problem? What is that telling you? Tell me. What is x in this problem? It's the size of square you cut out. Good. Tell me what the 649 is. That's the volume. So that's the biggest volume you can possibly make, see. Okay? So what you would have for your answer then is you would just say, and you can just round to like 1 decimal. This is about 3.2 inches roughly. And then the maximum volume is about 659.5 cubic inches like that. Okay, so that's how that goes. A typical kind of calculus problem. In this class, we got to use technology because we don't know about derivatives and stuff like that. That's what you learn in Calc 1. Okay, does that make sense? Everybody okay? Any questions? Everybody doing that okay with your calculators? It's new to some of you, so if you need to come by and get a little help with your calculator, please do that. All right. So we're going to look at 3 examples. That's kind of one of my favorite ones to do. It's pretty easy to understand. The function's pretty easy to build. Okay. So let's go to the next page. And then this is the next one that I picked out. Example 2. So what we're going to do on this one is, the building the function on this one's a little bit harder. But what the problem says is you've got the graph of y equals square root of x, which I went ahead and have on your handout. Do I have this picture on your handout? Okay, good. So that kind of helps a little bit. Then what we're going to do is express the distance from the point to the point 1, 0. Okay? So here's what you want to do on the graph that I gave you. Go ahead and just put the point right there and label that 1, 0. Okay? And then the other thing that you want to do is pick a dot somewhere. It doesn't matter on your curve. And you want to call that's the point P, which is xy. So that's an arbitrary point. So let me kind of explain it this way. So what we're doing, this is when you're here, the distance from there to there is that line. If we go further out that way, the distance from that point to that point gets bigger and bigger forever, right? Okay? If you're like here, the distance is 1, but that distance somewhere, maybe like around here somewhere, that distance is the smallest possible. Does that make sense to you? Okay, so what our job is to figure out what point specifically on the graph minimizes the distance to that point 1, 0. Okay, that's the ideal. So there's a couple of things that you would want to know to do this. First thing is I would just draw a line, and let's call that D for distance. Okay, and let's see from your past how many people know this. Did you ever learn a formula that finds the distance between 2 points? Does that sound familiar to any of you? Okay, all right. I'm going to write down what that formula is. And this is a formula that anytime you have 2 points, you can use the distance formula. Okay, so the formula goes like this. It really is derived from the Pythagorean theorem. If I had a little more time, I'd show you the derivation. But what you do is you just take the x values, whatever they are, and subtract and then square. And then you take the y values, whatever they are, and then you square like that. See, it's really a Pythagorean theorem. You're doing the square root of a squared plus b squared is what you're doing. Because this thing right here can be made into a right triangle. And it turns out that this part right here is a, and that's b, and that's c. So you're doing, this part right here is the distance from that x to that x. This distance here is that y from that y, like that. So it's really the Pythagorean theorem is what you're doing, okay? So let's put this together. So what you want to do is take these 2 points and then put this in the distance formula. All right, so we're going to go like this. First of all, subtract the x's. So you have x and you have 1. So you would just say x minus 1 squared. You could also do 1 minus x. It doesn't matter. and then do the y values the same way. That will be plus y minus 0 squared like that. So that's the distance formula. Now, we're not going to multiply this stuff out very much because you're going to use your calculator anyway. So what we would end up having is, this would be x minus 1 squared, and then that would be y squared, so it would go like that. So that's what your distance is, all right? Now, what we're trying to do is get a function that we'll put in our calculator and graph, and then find its minimum. Okay, one thing that's real important on this is, at this level, whatever you put in your calculator can only have one variable. Right now it has x and it has y. You want to just have x in there, all right? So there's something you can do. There's something you know about y. If you look at the original problem I gave you, what did it say y is? It's the square root of x. Okay, so what you're going to do is you're going to take that and plug that in right there. And then that way your equation has one variable. So you can't graph something if it's got two variables. So what you want to do is you would have d equals square root x minus 1 squared. Now replace the y with square root of x and then square it. Does that make sense what I did? Okay. One variable. That's real key when you're doing these problems. Yes?
Wouldn't the square root of x squared just be x?
Yeah, that'll be x. Okay, then we're done and we're ready to put it in our calculator. Yeah, so you can simplify that piece. Now you can FOIL that out if you want to. I'm just going to leave it alone. Then we have plus x like that. Okay, like if you were in calculus, you'd multiply it out, you'd do the derivative, something called the chain rule and all that kind of stuff. All right, so that is the function. The hardest part of these problems is getting the function. Does everybody understand what I just did okay? Okay, all right, you got to know the distance formula. If that's new to you, make sure that you write that down and try to understand that it's really the Pythagorean theorem. All right, so we're going to go now to our calculator. So you want to put in stuff with me and see if this is working okay. All right, first of all, put in this in blue, and you're just going to go like this. We go y equals square root, and then parentheses x minus 1 to the second, and then plus x. Okay, there's no sense to multiply it out because if you make a mistake, then everything's going to be messed up. Okay, now for a window, we got to rethink the window from the previous problem. Now, first of all, if you look at this problem, you know, the distance is always going to be some positive number. I would go 0 to just something. I'm just going to try a number and kind of see. Let's play with this a little bit. And another good thing to do before you do your window is look at your table, and that will help you figure this out. So I'm going to go second graph and just look at this. Okay, now here's what this means. If you look at your table, that means if x is 0, then the distance is 1. And that should make perfectly good sense to you. If x is 0, the distance from there to there is 1, right? Okay. The second thing, if x is 1, the distance to that, to that point is 1. And then if you go out to 2, it starts getting bigger forever. Okay, and what's going to happen is that distance from that point is going to get bigger infinitely. So what I would say on here is let's try this. Let's go, and it looks to me like we're looking at the minimum distance, and you're probably going to have some fractional values. So what I'm going to suggest, we start with 0. Once you get past 2, it just starts getting bigger and bigger. So I'm going to go 0 to 2, and a good way to scale that probably would be by a half or something. And then for your y's, we would probably go 0, maybe the same thing to 2 by 0.5, okay? And all we got to do is look at the graph in such a way that you'll see a minimum on it, okay? So let's try the window like that. So let's set up, go to window and go 0 to 2, scale by 0.5, and then do the y's the same way, 0 to 2, and then scale by 0.5. Okay, now graph, and then let's see kind of what we have here. Once you got everything set up, this is what this is going to show. Okay, and this makes sense to me. What this graph is saying is at some point in time, that's going to be the shortest distance, and then it just gets bigger forever. Okay, Now that's a graph of the distance function that we did, so you need to find that minimum to solve the problem, okay? So on the graph, let's just do this like this, and a sketch is okay on this. Let's just go something like maybe every 2 is 0.5, or whatever you want to do there. And then same thing here, maybe every 2 is 0.5. And then if we get 3 points, that's good enough. Okay, so here's kind of what I see on this. Now you can trace on this if you want to. So like if you trace at x equals 0, that gives you the point 0, 1. So basically if we just get the first point, the last point, and then find the minimum, then we're okay. Then I'm going to trace it 2. So if I trace it 2, just for estimation, that's about 1.7. Okay, so at 2, it looks like we're up about roughly 1.7 like that. And then we'll go ahead and do the minimum. Okay, so you're ready now to do your minimum. If you got your graph in your calculator, then what you do is, again, you go second, trace, and then this time you're going to go to the minimum, press enter, and then it's a matter of getting left and right bounds. Okay, my calculator's a little bit slow with this cursor key on here. So you just move over until you know you're to the left of where that minimum is. And then that will establish that left bound. Come on, this thing is so slow. Okay, it doesn't matter where, as long as you're convinced you're to the left of it, you're good. Okay, so I press enter. Now I do the right bound, use the right cursor key, and then press enter when it says guess. And then that'll give you the minimum value right there. Okay? Okay, so there's your minimum right there. Okay? So again, what this means is, what is the meaning of that 0.5? What does that mean to you? On my graph, what's that going to mean? On this graph, what does it mean? If x is 0.5, what happens? The distance is minimized. Okay, from there to there, that distance is minimized. Okay, so what you would end up having on this, what values of x is the distance the smallest? That would be 0.5, and then that distance would be about 0.87 is what that is. So what's happening on this then, if you go through and just plot this point, over 0.5 up 0.8, that's what the graph looks like, and then that's your minimum right there. All right. So what this is saying is, if you took this point right here on the original graph, if you looked at that point right there, that distance right there that I'm drawing in the green line would be the smallest distance that you could ever hit. Now that looks rational to me. How about to you? Okay. All right. Because once you get beyond that 0.5, it's going to get bigger both ways. Distance is going to increase. Okay, that's a little harder problem than the first one, but the key is once you get your function set up, then it's a matter of just going to your calculator and getting that worked out. All right, does that make sense? Tell me. I don't have any idea if it makes sense to you. Makes perfectly good sense to me. Thumbs up, thumbs down, thumbs sideways. Okay, good. All right. Okay, let's go ahead and do this last one here, and then we'll take a break. What I gave you on your homework is just similar problems. The idea is kind of getting used to this to kind of help you with Calc 1. All right. Okay, let's see. Ready to go to the next one? Everybody with me? Okay. All right, so I picked out one other one here. Some of the problems in this book are really good. I tried to just kind of pick the ones that were kind of average and not the real complicated ones. You'll see a little bit more of that in a Calc 1 class. Okay, so what this one is saying is you have a rectangle that's inscribed in a semicircle, and that semicircle has a radius of 2. I've got the figure drawn out for you, and you're going to let P be a point in quadrant 1 that is the vertex of the rectangle and is on the circle. All right, so first of all, what you have is this is the graph of the function. The semicircle is the square root of 4 minus x squared. That's given to you. Right? And what's going to happen is, as you change this point, as you move this point the rectangle changes, doesn't it? Okay, so like if you move this point way over here, well, the rectangle just sort of flattens out, doesn't it? If you move the point up there, then the rectangle kind of becomes tall and skinny. So the rectangle is defined by that point. So what you're going to end up doing is finding the area that's the biggest, and then you're going to find the perimeter, I think, that's the biggest also, all right? So the whole key to all these problems is to set up your function and then set that up with one variable, all right? So the first thing we're going to do is we're going to look at the area. All right, so first of all, if you find the area of a square, well, you know that you just do base times height, right? That's how you find an area of a square. So what's going to happen on this is this, and you have to understand this point xy is arbitrary. So one way to look at this is this part right here, from there to there is going to be x. Okay, from here to here is also going to be x. So therefore, that entire side is just going to be 2x. Okay, like that, all right? So you just double that x to get 2x. Okay, and then what happens on the height is, what's the height? It's not 2x, what is it? It's a y value, what is it? It's just y, exactly, okay? Only y. So the height of the rectangle is whatever y is. It's a y value. But the width is you're doubling the x. So what you'll have on this then is when you put your function together, it'll go like this. So we have area is the base. The base is 2x, okay, from there to there. The height is y, so therefore you get 2xy. Okay, that's what the area is. Now, we can't put this in our calculator. How come? What's wrong with it going to the calculator right now? It's got two variables. We can't have it, so you got to get it down to one variable. Any suggestions what I can do to get it down to one variable? It's kind of like the last problem. Plug it in, exactly. Here's what I gave you is this thing right here. I gave you the function, so that goes right in there. Okay, so what you'll end up having, and I'm going to say a of x. I'm going to say a function in terms of x, so we would have 2x times square root of 4 minus x squared. Okay, so that is your area function right there. Okay, that's what we'll model the area, and that's what we'll put in the calculator and look for a maximum on. Is that logical to everybody? Base times height. Okay, so you got to look at your diagram, figure out what base times height is. Okay. All right, so now we go to the calculator, and then we'll put this in. So just put it in the way it is, 2x. And then put in square root of 4 minus x squared. And then we'll take a look at that graph on there, okay? And let's see, I'm going to use the window from the last example, and I'm probably going to need to adjust that a little bit. So probably the x is probably okay. So we could just go 0 to 2 like we did on the last problem. But the y's need to be bigger. Again, if you don't know how to do your y, go second table and just look at the biggest y right there. So it looks like somewhere close to 4. So I'm going to suggest that we just go 0 to 4 like that on our window, and then let's graph it and see if we can see a maximum on there, okay? We can always adjust if we need to. Okay, now this is not graphing the semicircle, it's graphing the function for the area, okay? And what's happening on that, it's kind of an interesting looking graph. What's happening is that's your maximum area right there for this particular problem, okay? So let's go ahead and just kind of draw a sketch. I'm going to just do something kind of, let's see, we want to go all the way out to 2. Let's do something like this, 1, 2, 3, 4, 5, just whatever you want to do. 2, 3, 4, 5. And then up here we'll go up to 4. Okay, then just 3 points is good enough. Okay, clearly what we have on here is you got a point there, then you have a point there. Okay, that's coming up. Now just do your maximum on your calculator. So again, you go second, trace, go down this time to option 4, which is the maximum, and then get your bounds. Okay, that's a good left bound. Okay, get a little bit to the right of it. Like I said, it doesn't really matter where as long as you know you're to the right of it. Okay, press enter. When it says guess, press enter again. Then that'll give you the point right there. All right. So what you get is this is 1.4, and then that's 4. What this represents is this is the x and y value. That's the x value that you're going to use on your function, and then that's the area of the square. All right, so what you would have, you can just plot that point. So it's about 1.4 and all the way up to 4 like that. So roughly this graph does something kind of like that, with that being your max. Okay? All right, so that would be the idea. So what values of x is the area the largest? X equals 1.4. That's actually probably the square root of 2. If you did this with calculus methods, you would probably get the precise answer, which I suspect is square root of 2. Okay, like that. All right, so if x is 1.4, that makes the rectangle have the maximum area. Does that make any sense? Okay, because what's happening is the rectangle changes as x and y changes. X is what determines what that area is. Okay. Any questions? These problems are fun. To me, they are. I don't know about you, but they're interesting. Okay. Optimization's interesting stuff. Okay, let's do one more, then we'll take a break. And the last one I wanted to do is the same problem. We're just going to do the perimeter, and we're going to look at the same diagram again. So in your diagram here, perimeter, you just add up all the sides. Okay, so, or you can do like this. The perimeter of a rectangle is just 2 times the length plus 2 times the width. Okay, you just double the length, double the width, and add them up because you're finding the distance around the square. So it doesn't matter which is which. So basically on this, if you look at this piece right here that I'm highlighting in blue, that'll be, we'll just call that the length. Okay, that length is what? It's 2x, the same as it was on the last problem. So what you would have is you would have 2 times 2x. Okay, the length is 2x in our diagram. Okay, the width was y. Okay, so this would be plus 2 times y, like that. Okay, same thing as the last problem. The length's 2x, the width is y. All right, so what you'd end up getting is 4x. And then what do you do with the y? Same thing we did on the last problem. Take the function value, this thing right here. That's the graph. And then plug that in for y. That way you've got this down to one variable. So we'll just replace that with 4 minus x squared like that. So the perimeter function is 4x plus 2 times 4 minus x squared. Okay, then that'll give you a model, a mathematical model, that will help us maximize the perimeter. Does that make sense? Okay, all right. So put it in your calculator and just do the same thing. Okay, we'll just do, I don't care on this one about the graph. Just go through and do, I think I had a graph on the next page. Don't worry about the graph. So let's just put this in. So I got 4x plus, let's see, 2 times the square root of 4 minus x squared. We'll try the same window and just see if the same window works okay. So I'm just going to graph it. Probably need to change that. The perimeter is quite a bit bigger. Okay, so let me make sure I got everything in there right first of all. Okay, I want to go to my table. Okay, yeah, the y values have got to be bigger. Okay, so I would suggest that we go, same thing on x, we can probably go 0 to 2, but y we probably need to go up to about 10 or something like that. Okay, the y values are getting bigger, and once you get past 2, you start probably doing a square root of a negative number. That's why you've got all those errors in there. So let's go 0 to 2 and maybe 0 to 10, like that. And let's see if we see a graph. There we go. Okay, as long as you see the maximum, that's all that matters, all right? So what happens is we just need to do the max there, and then that'll give the max perimeter. So again, it's second trace, option 4, and then do your left and right bound. And you got it. Hardest part of this problem, these problems, is getting the function put together. Key thing is make sure it has one variable, then graph it, and then do this with technology. Okay, so let's see, here's my right bound. And let's see, the answer will pop up here. So here's the idea. So what you would have is if x is equal to about 1.8, then we would end up having the maximum perimeter would be equal to about 8.9. Okay, that's what happens. So if x is around 1.8, that makes the rectangle have the largest perimeter. So it's a little bit different than what we got on the area. That's the idea. Okay? Is there any questions about what I'm doing? How many people did this kind of thing in high school, like in calculus? A lot of you took calculus, right? Does this look familiar to you, kind of, if you took calc? Okay? All right. Okay, these problems are basically just taking some situation and modeling it mathematically, then using your technology to find max or min. Okay? All right, so I'm going to close this off and go ahead and take a 5-minute break.